Hi, I'm Matt, and I'm presenting on behalf of Team Ambitious Engineers. So, a bit about us. I'm a first year PhD student at the University of Washington. I have prior industry experience as a data scientist, in particular at a startup called Shifted Energy, where I've done a lot of energy forecasting. My teammate Sorpang is a master's student at the University of Hawaii, and he has prior industry experience as a software engineer. He was also responsible for coming up with our team name, so you can thank him for that. A bit more relevant background about us. He and I met while doing a water heater optimization project at the University of Hawaii. And I went on to do my master's thesis on water heater optimization. And this is relevant because you can think of a water heater as a type of battery. By design, water heaters store energy. We can tell them when to charge. The only problem is that they discharge randomly. We need to wait for someone to use hot water. And they're also leaky in the sense that they lose some of their energy to the environment. So they might not be the best battery, but we found that a lot of techniques that you can apply to water heaters, you can also apply to batteries. And so I think this experience was really helpful for us in this competition. So here's a high-level overview of what I'll talk about. First, phase 1, we decided to break things up into single-agent optimization followed by multi-agent corrections. So for the single-agent case, we optimized things with dynamic programming. The main challenge was handling the grid costs, which were non-causal. In particular, the grid cost at the current time step depends not only on our current action, but also on future actions. So instead, we optimized with respect to a proxy cost. And the idea here is to penalize actions that lead to large energy consumption. So in particular, our proxy cost starts off like the average cost, but then we add these penalty terms. So we penalize the group's net energy, the absolute value of that, the net energy squared, and net energy cubed. And then these proxy weights, they're just parameters that we tuned. So once we had the single agent actions, we tried to improve them with a multi-agent model that took into account group info. So in particular, we trained a multi-layer perceptron, or MLP, with CMA-ES, which stands for Covariance Matrix Adaptation Evolutionary Strategies. And so basically we just used that as a black box optimizer, mainly because it was easy to use. It worked basically off the shelf, and it was fast. It was parallelized. And so the input to our model was the current observation. We fed in single agent actions and converted them to energy usage. And then we calculated group features like the total energy consumption, the total energy consumption of the previous time step, etc. And we also fed in future values of like solar generation and the price for power. Phase 2 and 3, our approach was very similar to phase 1. The main difference is that we needed to replace future values with forecasts, and instead of DP, we used an MLP. So for forecasting solar generation, we kept things simple. Again, we used an MLP, and we trained it with SGD. The input to this model was the lags for each building's solar generation. And then we also found it helpful on the public leaderboard to use the average phase 1 solar generation and look at future values or leads of that. And so you can sort of think of that as like a leak, because we don't have future values in real life. But the reason why I think it helped in this case is because if you look at the solar profiles, they're all highly correlated with each other, and it's probably because these buildings were probably at like the same location. Forecasting the non-shiftable load was similar. Again, we use an MLP. Here the input was a little different. We used lags, but we found that the leads weren't very helpful. And we calculated seasonal exponential smoothing features. Basically all that is an exponentially weighted moving average. And the seasonal part just means we use different groupings. For example, we calculated the average non-shiftable load on Mondays at 10 a.m. So the optimization part of it was very similar to phase 1. Again, here we have a single agent model. The difference is that we use an MLP rather than DP. But again, the single agent actions are fed into a multi-agent model, which learns to adjust the single agent actions. This was trained end-to-end with CMAES, and the input to these models is pretty much the same as phase 1, except we replaced future values with forecasts. So to conclude, this is a high-level overview of our approach. This slide's not meant to be very detailed. It's mainly meant to sort of show the similarities between the two approaches. So in phase 1, we trained a single agent model, and we optimized it with dynamic programming. We fed the single agent actions into a multi-agent model, and we also gave it group info. And this multi-agent model tried to correct the single agent actions. In phase 2 and 3, the approach was similar. The only difference is that we replaced DP with an MLP, and we replaced future values with forecasts. And this dotted line here, that just shows that we trained everything end to end. So what we didn't do was train the single agent models separately and then feed those actions into the multi-agent model and optimize the multi-agent model. Everything was trained at once. Some things that we thought of but didn't have time to try. At the end of the competition, we realized that there was like probably some low-hanging fruit for feature engineering. We probably should have been calculating like running monthly energy consumptions and calculating the max for that month. That probably would have helped us optimize the grid costs. On the forecasting side of things, you might have been wondering why we were using an MLP, not something fancier like an RNN or a CNN. And it's mainly because it was fast and easy to use. We did try an RNN. We got roughly the same results as an MLP, but the MLP was like 10 times faster. But we do think that we could probably improve the forecasting with a better architecture. For modeling, we wanted to try model predictive control, but we had all the ingredients, just not the time for it. And for optimization, RL seems like the natural method to use here, but we kept things simple. We used a black box optimizer, but it seems likely that RL can probably do better here. So that's all I have. We'd like to thank the CityLearn and AI Crowd teams for hosting this competition. I think having a simulator is very important for these types of optimization problems. I think having a competition is a great way to benchmark techniques and promote ideas. So thanks again, and thank you for listening to our presentation. Thanks.